I'll wait for your cue. Is the voice okay? Hi, everybody. Welcome. It's March 23rd, fall semester 2017. I think it is, Chris. I'm not certain. I think that's when it is. This is our review for Exam 2. So, Gabrielle, I'm looking forward to this review session tonight. We're filming this on Thursday night. Now, we have our lecture tomorrow. Now, it turns out the exam is going to cover chapters 4, 5, and 6. In terms of the lecture, we have not yet covered all the material you will be seeing tonight. So, for those of you here in the studio audience, you're going to be seeing material we haven't yet covered. For those of you on the archived recorded session, as long as you showed up to tomorrow's lecture, which I don't know if you will or not, but hopefully you do, you will have seen this material. So let's just dive into it. My goal for tonight is to get you ready for the exam. And the best way I know how to do that is let's do an exam from last semester. So let's do exam 2, which is posted on the Canvas course website. It's exam 2 from the fall 2016 semester. All right, so why don't we just dive in and just do it. And I think the first problem is one we haven't covered. So we're going to get our feet wet, diving into the deep end of the pool. Okay. All right, now this we haven't covered, so I'll step you through it, and you can do this. I'm confident that you can do this. We're going to be doing something called Gaussian parameter estimation, which is one of my favorite things in Chapter 6. Now, it turns out that all the formulas I think you need to solve this problem are given in the exam. Okay? So if you permit me for just a moment, I know you're copying this down. Let me just to give us all confidence, if we go to the end, we have a formula sheet. Okay? And I also give you the tables that you'll need to figure all this out. So the formulas as well as the required tables are all given. Okay? So let's just start. Now I need your questions as we go through this if I'm not making sense. So it turns out that a colleague has sampled a large population. And from this, they determine an estimate on the population mean. Now, this we have briefly discussed. I have a large population. I think I might have used the example of like a wireless phone. And we want to find out, let's say, the average lifetime of a wireless phone made by Apple or Samsung. We can measure the entire population. No one does that. Too long. Okay? So what we do is we measure a sample. And the question becomes, can I estimate the mean of the population from measuring the mean of the sample? And the answer is yes. Okay? That's what Gaussian estimation is. So what happens is a colleague of yours has estimated the mean for a population, the mean lifetime, the mean transmit power, the mean whatever it might happen to be, as falling between 14.3 and change up to 15.2898. Right? Now, as we will see tomorrow in lecture, this is the formula that you use. Okay? Mu, that's the mean of the population, is X bar. Anyone guess what's X bar? That's right. I heard you say it. It's the mean of the sample. Okay? So X bar is the mean of the sample. So mu equals X bar, but not exactly. There's plus and minus some tolerance. Right? So we take plus and minus some tolerance, and the tolerance is Z alpha over 2. That looks like I got to look it up on the table. Okay? Times the sigma over the square root of n, where sigma is the standard deviation and the square root of n. N is the number that we measure in our sample. How am I doing so far? All right, good. All right, now, it says here we're 85% confident of the result. You know what that means? That means we're 85% confident that the real mean of the entire population, which is unknown, falls in that interval. Okay? So I say, okay, so that's the real, that's the mean and the interval. Somewhere the real mean is in there. How confident I am? 85%. I tell you the standard deviation is 2.7. What is the sample size? Okay, so what I don't know is n. Okay, so my colleagues, this is step number one. Now, I know you're seeing this for the first time. I want questions. Okay, if I'm not clear, I want your comment. So here, the formula says mu equals x bar plus and minus z alpha sub 2, I have no idea what that is. We'll get to this in just a moment, times sigma over the square root of n. All right? What am I looking for? N. Now, help me out. How do I get x bar? I mentioned it here. Does it make sense? I give you the interval, 14.3102 to 15.2898. Where's x bar? Chris?
You're so generous. It's right in the middle.
Perfect. It's right in the middle. How do I know that? Chris, you nailed it in one. It's right in the middle because mu is x bar plus and minus some number. It's plus and minus the same number. So x bar is in the middle of the interval. So I say, great, I find the middle. X bar is 14.8. Okay? All right, I'm getting there. Remember, what's the unknown? N. All right, so I now know x bar. So I can now write that interval as 14.8 plus and minus a number. Am I okay so far? Chris, you're smiling. Is this so far so good? All right. Our aloha symbol. Okay. All right. So I now know that z alpha over 2, whatever that is, times sigma over the square root of n is 0.4898. Are we doing okay? Good. Now, okay, I got to look something up in the table. Okay? So it's related to this 85% confidence interval. My colleagues, remember, what does 85% confident mean? It means that I'm 85% confident that the real unknown mean of the whole population is in that interval. So I say, okay, Gaussian. Oh, that's the bell-shaped curve. Now, I need your help on this because for some of you, maybe most of you, this is your first time seeing it. You'll see it again tomorrow during lecture. But I want to make sure this makes sense. This is the bell-shaped curve. This is the Gaussian distribution. Now, I'm 85% certain that I'm in a certain interval. X bar plus and minus something. So that means the area from here to here has to be 0.85. That means the interval of one side is 0.85 over 2, which is 0.425. Now, you might be saying, why do I have to figure out half of it? Because the author of our book only gives us the single-sided z-tables. So this z-table is going to tell us how to find the area and how to find the numbers we need. So I don't use 0.85 because I don't have a double-sided z-table. I have a single-sided z-table. So I take 0.85 divided by 2. Now, z alpha over 2, that's a subscript, not a mathematical division. Z alpha over 2 is the number that gives me an area under the curve of 0.425. Am I okay? So I say, okay, I now go to the z table. Dun, dun, dun. And what I want is to figure out what this number is such that the area from 0 to that number is 0.425. How am I doing? Home audience is quiet here. Okay, all right. The studio audience is deep in thought. Where do I run to now? The Z table. Ah! All right, what do I need? What was the number? It was 0.85 divided by 2. What was that? 0.4? 0.425. Help me out. Where is it?
So you're looking, I see 0.242 there and 1.4, and then you use the top row.
Yeah.
Narrow in your circle.
Exactly. And Chris, if I could add to your comment, I know some people in the home audience are very concerned right now. They're saying this is not 0.425. This is 0.4251. Oh, come on. That's close enough. So we don't have to interpolate. Come on. We've been colleagues now for 2 semesters. We don't have to interpolate. So here's what we get. 0.4251. So pick the closest. And Chris, I'm going to do exactly what you said. But to do it, Chris, I'm going to get it so we can read the top column. So 0.4251. So what Chris said, that is 1.4. 0, 1, 2, 3, 4. 1.44. Did I do okay? My 2 gentlemen here, am I doing okay? My colleague here, we're good? So what I get is Z sub alpha over 2, it's a subscript, is 1.44. So what we have just found out, whoops, too far, is the number here such that the area from 0 to that number is 0.85 over 2. And that number is 1.44. My colleagues, you're great if you're getting this, because I'm hitting you all this on the first time here. So now we plug this in that I know, where am I here? This is the 0.4898 upper right-hand screen. That was the value of Z sub alpha over 2 times sigma over the square root of n. I just found out Z alpha over 2. I was given sigma. We're home free. I now figure out n by solving this. And what we get is an n of around 63. Now let me pause. I thought that was a hard problem, especially if you're seeing it for the first time. How did we do? My gentleman here in the first column, in the first row of the second, how we doing? We got it? We're good. We're good. My right fielders, my short right fielders, we're good there? All right, good. So I say, great, that tastes, yes, sir.
What does mu represent?
Excellent. Question is, what does mu represent? Mu represents the mean of the population of everything. What we measure is X bar. And from that, according to this theory, since we, and I mentioned this briefly in the lecture before spring break, but that's okay, it's IID, independent and identically distributed measurements or experiments result in a Gaussian distribution. So the theory says, if I measure this enough, we get a Gaussian distribution. So that allows me to put a bound on mu. Not to determine mu, but to put a bound on it. And what we did here is that's the theory that we worked on. Did I get your question okay? All right, good. First problem, done. All right. That was a hard one. I don't think there was a part B to this. Okay. Now, for those of you who have had prop stats, you'll look at this and say, I got it. If you haven't had prop stats, I want you to look at this problem and by the next 5 minutes or so say, oh, I got this. All right, so I want you to feel confident you can do this. This is using a Gaussian random variable. Now, as I think I left off in the last lecture, right before spring break, let me just go over here to this whiteboard. The Gaussian distribution has this bell-shaped curve, and the middle is where the mean is. Now, it turns out if you want to know the probability of a random variable that is Gaussian falling between the two numbers x1 and x2, you take the area from x1 to x2 under the distribution function. In fact, that's a general principle for all probability distribution functions that are continuous. So we look at this and say, okay, it turns out it's a messy thing to integrate this function. So they have tables, and they're called z tables, and that's what we're going to use. Okay? So it says here, determine the probability that the random variable is less than 55.6. And I tell you that the random variable is Gaussian with a mean of 58.7 and a standard deviation of 4.9. Now, here's the only trick, and you only have to know this and you're home free. The people who worked on this integration did it numerically, and they said, look, I'm only going to do this once. I'm not going to do it for every possible combination of different Gaussian random variables. So I'm only going to do it for a mean of 0 and a standard deviation of 1. Okay? So that means what we have to do, and it's written there, and let me come over here. Let me come over here. Since the tables we're about to use are for a Gaussian variable with a 0 mean and a standard deviation of 1, we have to do this variable, this change of variable. So we're going to call it the z variable. Now that's x, okay, x minus mu. Oh, wait a minute. If I take a Gaussian random variable and I subtract the mu, what's the mu? My colleague here knows. It's the mean. It's the mean. So if I take a random variable and, Chris, I subtract the mean, I now got a 0 mean. And if I further normalize it or divide it by the standard deviation is 1. Now I can use the table. Do I give you this formula? Yes. Why? Because I'm a nice guy. All right? So I say, excellent. We now have the transformation. So I say, great. So on my second line there, z equals x minus mu over sigma. I give you that formula, but hopefully you understand it. 0 mean, standard deviation of 1. So I give you everything. What's the value of x? 55.6. What's the mean? 58.7. And then we divide by the standard deviation of 4.9. Now, we may have to use symmetry to solve this problem. Okay? So we want to know the probability that x is less than 55.6. Now, this translates into the z curve having a probability of less than minus 0.6327. So all we've done is instead of having to work with 55.6, we now have done a change of variables, and it becomes minus 0.6327. How am I doing? Good. We're doing good. Doing good. Now, I want to be less. I want to be less. So I'll meet to put you on. Just want to make sure we're okay. You're taking such good notes. I'm very impressed. Okay. So I want to be less than this. So the area I want is this area. I've shaded in here. Minus infinity out. From minus infinity up to minus 0.6327. How am I doing? Now, we're only given a single-sided z table. For those of you in prop stats, I think prop stats, you have a double-sided. On this exam, you're only going to have a single-sided. So what does that mean? I got to use a little bit of symmetry. You're going to be good for this. I want this area here. This curve is symmetrical about the origin. Okay? And the area is 1 from minus infinity to plus infinity. So this area from minus infinity to here, I claim, Gabrielle, make sure I say this right, is the same as this area to positive infinity because of symmetry. Okay? All right, so now what I want is this area here. Last trick. Last trick. Let's go to the z tables. Look at this right here. This gives us the area from 0 to z. What I want is the area from z to plus infinity. How do I do this? James, help me out. Chris, right? Did I say James? That's the second time I've called you James. You must look like a James I knew once. So forgive me, Chris. I'm so sorry. Chris, what do I do to get this to work?
Well, you do what you did, the reverse of what you did there. So instead of going to the table and finding z, you find your value, or the absolute value in this case, since we're getting a single one. So you find 6.6327 on the table.
Perfect.
And then you would backdate it until finding out what you need.
Perfect. So, Chris, if I can jump in, what you're saying is we can get this area here. All right? And I get that directly from the table. So, my colleagues, what you do is you look up in the table, and we'll do this together, 0.6327, and I get this area here. Okay? So, let me just go to the table. 0.6327. Help me to remember that. 0.6327. All right, so 0.6, I better slide this down. I'm not that tall to jump all the way up there. Okay, 0.6. Okay, 0.63. 27. Gee, I only go out to 2 decimal places. Is that okay with you? We stick with 2 decimal places here on this table? I think it's good. All right? So 0.6, what did I say, 0.63? Do we get 0.2357 in my solutions? All right? So I take the 2.2357. Now, last bit of trickery here, because I was trying to trick you on this one. The last bit of trickery. I'm just getting this so I can kind of reach it a little better. Okay? This area here, we just found out, is 0.2357. Now, that's not the area I'm looking for. I want the area from here to infinity. How do I get it? Easy. The whole area is 1. Because of symmetry, this area from 0 to infinity, positive infinity, is a half. I know this area. So the area that we want is 0.5, because the whole right side is an area of a half, minus the area we just got there, 0.2357. We got 0.2643. So the probability of x being less than that number is 0.2643, and we are done. That was the answer. So I think problem 2 was more manageable. If you're seeing it for the first time, people love this stuff. They're lining up. My colleagues in the home audience, we got people lining up to get in here. They're yelling, they're screaming. It's wonderful. Okay, so we got 0.2643, pardon me, as the answer. How are we doing? Good. How's my right fielders again? We're good. The gentleman drinking the coffee or the water, we're good? We're good. All right. Okay. All right. All right. On to problem 3. All right. So problem 3 is a bunch of short answer questions. I think we've covered all of these in class. So this shouldn't come as too much of a surprise. All right. So I look here and say, great. What are the 3 mobile software platforms that we discussed briefly in the lecture on smartphones? All right. Android, Apple iOS, and Windows. I had written Windows 8. They're now up to Windows 10. I think we accept either one for full credit. Those are the 3. Okay, short answer questions. We got all of that. Now, do you remember how to convert a decimal number, a base 10 number, to binary? Yes, you do. Chris, what do I do?
First, you take the number that you're given and divide it by 2.
Chris, I'm going to jump in there. That's it. You hit it. That's all I need to do.
If it's an even number, your dividend is even, it's a 0. But if it is negative, or if it's odd, it's a 1.
That's right. Exactly. And Chris, that's what I got to keep track of. Perfect, Chris. So, Chris, I gave you this really big number. I must have been in bad mood when I made this exam. Look at this. I gave you such a big number. 5,132. What do? Divide by 2. I get 2,566, remainder 0. Here, let me slide this down so I can point. I bet you you're all good on this anyway, though. Here. I take the number divided by 2. This is what I get. What's my remainder? 0. Put the 0 here. Take this number, divide by 2. I get this number, remainder 0. I take this number, divide by 2. I get this number, remainder 1. You keep doing it. You keep going. What better way to spend a Friday afternoon doing this, okay? Now, the only trick is, because if you go to make a mistake, this is how colleagues before you made the mistake. You have to read the number from the bottom up. Okay? And then it works. So this one becomes that one. So you read it up, you write it like that, you put answer next to it, and I'm happy. You got full credit. Are we good on this? All right. Okay. This is just short answer questions. Some of this is just memorization. There's not really much I could say here. Part C says 3 different A to D converters. Tell me 2 of them. That's in the notes. You're going to get that. That's fine. I'm up to part D. It's another Gaussian distribution. Okay? Says you're given a random variable that has a Gaussian distribution. Now determine the probability that we are in the interval mu plus and minus 2.75 sigma. I have to tell you, I like to draw this stuff. Okay? So what we have is a Gaussian distribution. Okay? Now, I want to know the probability that I am mu plus 2.75 sigma or mu minus 2.75 sigma. So I want to know the probability I'm between here and here. I want this area. Okay? So what I have to do is the change of variables. Z equals x minus mu over sigma. I was looking at my colleagues back here when I said that before. You know why. X minus mu gives me 0 mean. Then divided by sigma, I get a sigma of 1. Then I can use the table. So what I do is I take the value of x. Now, what's the value of x? It is the upper bound. Mu plus 2.75 sigma. I then subtract mu divided by sigma. Oh, excuse me. I'm pointing to the upper one. I did the lower one. I beg your pardon. Okay, it's mu minus. I should have been pointing to the lower one. I beg your pardon. I get minus 2.75. I now do the same for the upper value of x. Kevin, how am I doing back there? All right, Kevin, good. So, Kevin, I now use the upper value of x. So, x is mu plus 2.75 sigma. Gabrielle, I then subtract the mean and I divide by the standard deviation. I get 2.75. I now want to know the probability of being between minus 2.75 and plus 2.75. But I have a single-sided z-table. So what I do is I figure out the area from 0 to plus 2.75. And what do? Multiply it by 2. So I say, okay, great. What do? Let's go to the z-table to make sure we can do this. I'm looking up 2.75. So let's go to the z-table to make sure we are okay. All right, 2.75. I got to go a little lower. All right, here is 2.7. And then this is 0, 1, 2, 3, 4, 5. It should be on what I have in my notes, 0.4970. Okay? Now, what do? Multiply that by 2, and I got the answer. How do we do? All right, good. Part E, this is the opposite of the previous problem, instead of going from decimal to binary, we go from binary to decimal. Easy, 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 easy. All you do is you start on the right-hand side with the binary number, and that's the position 2 to the 0, then 2 to the 1, 2 to the 2, dot, dot, dot. So how much do I have? 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Oh, I counted wrong. Try it again. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So my colleagues, look at the number and look what I wrote here. 1 times 2 to the 11th, plus 0 times 2 to the 10th, plus 0 times 2 to the 9th, plus 1 times 2 to the 8th, and so on and so on and so on. Add it up, you get a number, you're home free. Okay. All right, so I say good. All right. That's 3 problems. How can I help, sir?
If numbers are using choose common, just specify that in the question.
That's an excellent question. If we use 2's complement. I don't think to preface my answer to your question, I don't think I've ever asked a question on a test where I've given 2's complement and said, convert it to binary, convert the binary number to decimal or decimal to 2's complement. So I wouldn't expect that. If I ever do give you a number, a binary number, and it's important to know that it's 2's complement, I will tell you. But I don't think in all the years I've taught this course I've ever given a conversion from decimal to binary or binary to decimal where it's been 2's complement. My colleague, you might remember 2's complement has the sign, the plus and the minus. So the first bit is a sign bit, just so we know it's positive or negative. Did I do okay? Perfect. Okay, let's go on to the next question, question 4. All right. All right, this looks like a lot of words. I don't know, a lot of words here. And we got to see if we can figure this out. All right. I guess this is the one time we can't skip a lot of words if it's on an exam. But okay, we have a lot of words, and it says we have a sensor. Sensor produce a voltage. There's a highest frequency in the output of that sensor, and we're going to want to convert this to a digital signal. Great. It says we also want to have a resolution error of less than 0.65 millivolts. Ooh, draw a block diagram. I didn't know we had to draw block diagrams. Draw a block diagram of this system. Okay? And it tell me everything that's important. So here's how I started before I show you my drawing. My colleagues, I give you this formula. You might remember, I'm hoping you do, from our discussion of resolution error. In an A to D converter, we have these samples. Think of a ruler, right? If you have a ruler that measures to ½ an inch, your biggest error will be 1/4 inch, right? Because you're going to fall right in the middle, right? If you look at it that way. So here we have 2 levels, and we're going to have a resolution error in the A to D converter. So I tell you, I ask you, can we make the resolution error less than 65 millivolts? So it turns out, if you go to the formula sheet, and we talked about how to figure out this formula in the lecture, that's the formula for the resolution error. Plus and minus a half, because if you fall in the middle, you can go up or down. This is V voltage, range upper, minus V voltage, range lower. I'm using the author's notation. Divided by 2 to the n. N is the number of bits. I say, good. So it says here, we're to pick n such that this ratio here, this left-hand side, is less than 0.65 millivolts. So I say, great. I know the upper voltage is 5, the lower is minus 5. So I have to make that less than 0.65 millivolts. So you can use logs, you can do trial and error. If you let capital N equal 12, it's too big. If I let n equal 13, it's just a little bit less. So what did I discover? To meet the requirement of the resolution error, n, the number of bits per sample in the A to D converter, has to be 13. Am I good so far? So I say n has to be 13. Great. Oh, Oh, ho, ho. This was what I was really looking for. This was chapter 4. This was what I wanted you to know. Because I ask you in the problem, I have a sensor and I have an ADD converter. How do I connect them? Don't just connect them together. Why? Anyone? Let me ask you this question. Suppose I were to remove this middle block and just connect the sensor to the A to D converter. That would be a bad design. Why? Sir? Yes. I'm pretty certain there's noise there somewhere. And the problem is I don't know the highest frequency of the noise. So if I don't sample fast enough, not only am I sampling the noise, but I'm sampling the noise too slowly. And what I get is what we call an alias or an imposter signal. So what do? I put in an anti-aliasing filter. Okay. So I say, okay, that's the sensor. That's the A to D converter. What do I know about the A to D converter? It's 13 bits per sample. Now, the output, the highest frequency of the sensor is 1500 hertz. So for our purposes, this isn't exactly correct, but it's close enough we can live with it. God bless. We're going to say that this low-pass filter, also known as the anti-aliasing filter, we're going to make the cutoff of this be 1500 hertz, which is the highest output of the sensor. So now, the frequency here, the highest frequency is 1500 hertz. What's my sampling rate of the A to D converter? Twice that. Exactly. Sort of 2. Way to go. Okay. So it becomes 3,000 samples per second. How did we do? My colleague here, I'm thinking of you. Are you in electrical engineering? Yes. Here, I'm wondering if you're thinking the following, because this is like a first order design or like a first pass, a first cut. There's a couple of problems with this that we don't need to get into, but let me just mention for the EEs with us. If I make the cutoff frequency 1500, and this might be like a first order filter, you might remember, my colleagues, that by the time we get to the corner frequency, we've already started to drop off. And if the output of the sensor is 1500 hertz, I think in the real world, we're going to want this to be a little higher than 1500 hertz. Second thing that comes to mind, I made a statement before, and it's on tape. This is, I don't know, this is going to get me in trouble. Or I guess tape is old-fashioned. Who uses tape anymore? Chris, I saw you looking at me, tape. So what we would have here is, I said the highest frequency is 1500 hertz. No. We still get a slow roll-off. I would have to have a very high order filter to get a very steep one. So the design of this system is actually more complicated than what I'm saying here, because I probably want a higher cutoff frequency, and depending upon the order of the filter, I'd like to choose a different sampling. So this is what EEs live for. This is good stuff. Did I do okay? All right. Good. Are we good? Please. Yes. Will the formula for resolution error be on the formula sheet? Yes, it's there. Great. Thank you.
Would we ever have to go to digital to analog?
No. Excellent question, Chris. The question is, would we ever have to go from digital to analog? No. Thank you. Thank you, Chris. Okay. Okay. Problem 5 and problem 6 deal with independence in probability. And this is something we discussed in one of our lectures. So the thing that I'd like to do is, okay, part A, I have to show you the figure first. Part A says n equals 4. And oh, I love this problem. I actually thought this was a fun problem, but like I've said before, I need a life. Okay, here we go. I got to rotate this now. View. Now I want to go clockwise, I think. Isn't this a fun problem? There's another eraser while you're copying here. I'll be erasing the board. There we go. This is better. Okay. My colleagues, before we do the problem, let's have a little sidebar discussion. I'll tell you how you can solve these problems. Here. Suppose we have two sensors in parallel. Input, output. Sensor 1, sensor 2. Suppose the probability of a sensor working is capital P. Now, for this system to work, I have to be able to go through from the input to the output. Okay? Now, I'm going to ask you, what's the probability of this system working? There's an easy way and a hard way. Here's the hard way, which we're not going to do. The hard way says there are three possible ways this system can work. Both sensors work. Top sensor works, bottom doesn't. Bottom sensor works, top doesn't. We could figure out those three probabilities and add them up and you get the right answer. It's a pain in the neck. Here's my trick. Figure out the system does not work. Okay? Figure out the system does not work. How does it not work? Both the upper path and the lower path must not work. So that means the upper sensor has to fail. If its probability of success is P, probability of failure is 1 minus P. Now, in the wording of the problem, I say this is all independent. That means whatever happens here doesn't influence here and vice versa. So that means we can multiply. What's the probability of sensor 2 failing? 1 minus P. So, my colleagues, 1 minus P, the quantity squared, is the probability of this system not working. What's the probability of it working? One minus that. Okay, nice. I love this. Okay. Did you run across this in statistics, sir? Yeah. Okay. Yeah. So I think this is a good way of solving it. Now, now that you've drawn the figure, let me rotate this back. Okay. I say let n equal 4 and figure out the probability of this system not working. Now, what we had were 4 sensors in parallel. So the probability of those 4 sensors not working is 1 minus the quantity 1 minus P raised to the 4th. And if I remember correctly, help me out, we had 2 sensors after that, right? So those other 2 sensors now have to work. So the probability of 2 sensors working is P times P. So the whole thing working is this times this. Let me stop. How did we do? Then I said, okay, what happens? By the way, here's my rationale for this problem. In a lot of systems, you want redundancy. You want like reliability built in, because no matter how high P is, if all you have are serial connections, you have a chance of failing. It's possible of failing. So I said, what happens if you let n go to infinity? So instead of having 4 in parallel, you got 10,000 in parallel. You got 100,000 in parallel. All right? So do you know the answer? Not math. Can can you get the answer just intuitively? If n goes to infinity, what's the probability of getting through that first set of parallel sensors? I think it's 1. All I need is 1 to work. And if I have 1,000,000 of them, I'm pretty sure I'm going to get through it. Okay? So what we do then is just take the answer from part A and generalize it. So if you have n sensors, what's the probability of the system working? Where I had 4, put in capital N. And now let n go to infinity. No worries. Hello. Well, we're having a wonderful, would you like to stay? We're having a wonderful lecture on prop stats. Oh, that's very, okay. What we have here is now letting n go to infinity. What's nice is 1 minus p is less than 1. Okay, a number less than 1 raised to a very high power approaches 0. So that goes to 0, and what we get is, what did I do wrong? My colleagues, help me out. What did I do wrong? Oh, yeah, this, right. I'm sorry, Chris, I froze here. That goes to 0. So I have 1 minus 0 is 1. 1 times p squared, I get p squared. Okay, good. Makes sense. Did we do okay? All right, good. All right, on to problem 6. Oh, we're just ripping through this exam. Another figure. Dun, dun, dun. Figure 2. Oh, man, what are we doing here? View. Rotate. Clockwise. Oh. A little different. Okay? Who can help me out? What's the probability of this system working? Make n, just keep n. What's the probability of this system working? Come on. What do you get? Do we have a brave soul amongst us? We do. I'm surrounded by brave colleagues here. I know you can do this. Here. What's the probability of this here, this group of n sensors working? 1 minus, am I saying it right? Now be careful. I need your help. It's 1 minus p quantity raised to the n. Okay. Now, I have 2 in series. What's the probability of that working? P squared. Can you now figure out the probability of the whole thing working? It's 1 minus 1 minus. Chris, what do you think?
Well, for the series where it's the 4 in parallel,
Yes.
you'd get 1 minus p, the quantity to the 4th, and then to determine the system working, it'll just be 1 minus.
Exactly.
Because since it's all in parallel.
Yes.
It's the quantity 1 minus p squared.
Yes.
1 minus p to the 4th is the probability of the system working.
Right. Chris, I think you said it right. As you can see, when I was writing this, I was getting a little confused. I was getting all mixed up. This is like convoluted thinking here. Chris, make sure I say this right. We let n equal 4. The probability of the bottom path not working, 1 minus p quantity raised to the 4th. Good. The probability of the upper path not working, probability of it working is p squared. Probability of not working is 1 minus p squared. So that's this. Now, this is the probability of not working, lower path, probability of the upper path not working. The probability of the whole system not working is the upper path and the lower path not working, which is this. Lastly, what's the probability of the system working? 1 minus that. Whoa! How did we do? Now, Chris, I let n go to infinity. What's the probability of the system working? Forget the math. Let the engineer in you come out. We had 2 sensors in the top half. We had n sensors in parallel on the bottom. I just need to get from the left to the right. I let n go to infinity. Chris, 1. Has to work. All I need to get is 1 sensor to work, and if I have an infinite number of them, I think it's going to work. Okay, so mathematically, let's figure that out. We just take the answer from above, replace 4 with capital N. Now, let n go to infinity. So what we get is 1 minus p, which is a number less than 1, raised to a very high number, n going to infinity. That equals 0. That cancels all of this out. Not cancels, but multiplies by 0. We got 1 minus 0, which is 1. Beautiful. How do we do? All right. Stunned silence. All right. All right. We're coming down the final third. My colleagues, you're great to stick with me. For those of you in the home audience, if you have a ticket to another show or a play, you're welcome to leave. And I'll stick here with Tariq. Tariq and I will hang in here till the end. We don't have much more to go, just 3 more problems. We're doing good on time. All right, now, I thought this was tricky. God bless. I wanted to give a Gaussian problem that kind of jazzed it up a little bit. So here we go. You have a Gaussian random variable. I tell you the mean, 33.9. And a standard deviation, 2.8. And I say, okay, the probability that that random variable is between 28.7 and an unknown number is 0.1371. Determine the unknown number. Okay. So, I think, well, where do I start? I have to do the change of variables because I'm going to use the z table. So I get z equals x minus mu over sigma. That formula is given on the exam sheet. So I take the value of x, 28.7, minus the mean over the standard deviation. I get minus 1.86. That's the lower value. The upper value is unknown, but at least let me write it down. x1 minus 33.9 over 2.8. Now, I had to think about this problem. It says here, what's this area from minus 1.86 to 0? Now, are you okay on symmetry? I'm now looking at this Gaussian curve. On the Gaussian table, which is in our notes here, remember, it's a single-sided table. Only goes positive. But because of symmetry, the area, was it minus 1.86? The area from minus 1.86 to 0 is the same as the area from 0 to 1.86. So find 1.86 here. Got to slide down a little further. Find 1.86. Did I do it right? 0, 1, 2, 3, 0, 1, 2, 3, 4, 5, 6. 0.4678. Did I do it right? One more over? I'm all confused. 0, 1, 2, 3, 4, 5. Oh, no, you're right, 6. Right? Did I? Wait. Here, this is 1.80. 1, 2, 3, 4, 5, 6. 0.4686? Thank you. All right? So that's the area, 0.4686. So I come back here and say, got it, 0.4686. All right. Now, since the area, this is where I had to think about this. This, I think, was subtle. This is where people got stuck, so help me out. Since the area from Z1 to 0 is 0.4686, and we are given that the area from Z1 to Z2 is 0.1371, it turns out that my other number is negative. Let me say that again. I know the area from Z1 to 0 is is 0.4686. I'm told the area between my two numbers is 0.1371. Has to be on the left side. All right. So now using symmetry, I want this. Now what do I know? I know that area. It's 0.1371. How do I know that? I was given. Okay. So I know that's the area, 0.1371. Now, what do I know? I know the area from 0 to Z1 is 0.4686. How am I doing? I think we're almost done. Therefore, the area from 0 to Z2 has to be 0.4686 minus what's in the middle, 0.1371. I then look up 0.3315 in the Z table, 0.3315. Let's look it up, 0.3315. We don't have to interpolate. 0.33. Oh, it's there. Oh, how nice. So I think this is, I'm not able to read this here, 0.96. Okay? So that's 0.96. I say, I think we got it. I think we got it. I have to remember that what I found was the absolute value. So the real value of Z is minus 0.96. Plug that into the formula we had on the second or third line down. Solve for x1, and we did it. I thought this was hard. How do we do? Two more problems, and we are done. Problem 8. The binomial distribution. Now, this we have already covered, the binomial distribution. What are the three properties that have to be true for a system to display a binomial distribution? Classic example is tossing a coin. So what has to happen? We have to have independent trials. Second, only two outcomes, pass, fail, heads, tails, 1, 0. Lastly, for every trial, the probabilities remain the same. Now, Kevin, the hardest part about these problems for me is careful reading. I don't know if you have this problem. I got to read these like twice. We select 8 sensors. The probability of a sensor working is 0.8. Determine the probability 6 or more working sensors. That means 6, 7, and 8. So I look here, and that's 8 choose 6, 8 choose 7, 8 choose 8. Now be careful, set this up right. Probability of a sensor working is 0.8. So this is 0.8 to the 6th, 0.8 to the 7th, 0.8 to the 8th. Now if I have 6 sensors working, 2 sensors are not. Probability of the sensor not working is 0.2. If I have 8 sensors working, I have 1 not working. If I have if I have 7 working, 7 working, I have 1 not working. If I have 8 working, I have 0 not working. And I go through this, and I get an answer. How did we do? Are you okay on the binomial distribution? All right. Using the binomial distribution, part C now. Determine the probability less than 2 sensors working. That means 0 working or 1 working. Okay, so less than 2 working. So that's this probability here of 0 working or 1 working. So 8 choose 0, 8 choose 1. 0.8 to the 0, 0.2 to the 8th, and so on. 0.8 to the 1, 0.2 to the 7th. I'm looking around to see if there's any questions. Last, we have N sensors. Now this, I think I had to think about. I think. We have N sensors. All right. The probability of a sensor working is 0.8. Determine an expression. There will be 3 or more working sensors. Trick is here, I don't tell you N. So I want to know the probability of 3 working, or 4 working, or 5 working, all the way up to N. How do I do this? 1 minus. 1 minus the probability of 0 working plus 1 working plus 2 working. All of this has to be added and then subtracted from the 1. And there you have it. We have the last problem to come, and that's it. We did problem 8. Anything here on binomial I can help with? All right. Okay. You're great to stick with me. All right. I think we're up to problem 9. We are. Okay. All right. All right. Now, my colleagues, the last problem says the following. Gaussian parameter estimation, how we started this review session. That requires us to choose a sufficient number of samples to get a Gaussian distribution. Turns out, in tomorrow's lecture, I'll show you that, or I'll mention that that number is agreed upon to be 30. So if you sample 30 or more, it follows a Gaussian distribution. If you sample less than 30, it follows another distribution. That other distribution is called a student T distribution. The last problem here, if I remember correctly, is a student T. But it's almost the identical formula. The only difference is the table is different. Okay? So we do this and we're out of here. So, determine the average transmit power for a new wireless sensor. You measure 14 sensors. What do I know? 14 is less than 30. This is a student T problem. Okay? The standard deviation is 5.7. They tell you that mu is somewhere between those two numbers. Now, I'm reminded of my colleague's question before. What's mu? Mu is the mean of the population. Do I know mu? No, I don't, because I didn't measure everything in the population. So what is the formula? Mu equals x bar plus or minus t sub alpha over 2. S over square. Looks very similar, except instead of sigma, I use S. It's still the standard deviation. The key is, Gabrielle knows this, it's T. The T table, the student T table, not the Z table. Now, as Chris told us, where is X bar? In the middle. So I figure out the middle, 43.8. Now, what do I then know? That interval can be written as 43.8 plus or minus 2.6979. Okay, all right. That means that the 2.6979 equals, see, I'm looking up here, mu equals x bar plus or minus something. That 2.6979 has to equal t sub alpha over 2 times s over the square root of n. All right. N is 14, s is 5.7. Solve for t alpha over 2. I get 1.771. That's not yet the answer. The answer is here. I'm down to here. How are we doing? All right. Okay. They're coming back. I wonder if they're going to walk through here. If they do, we should ask them to sit down for the rest of the lecture. All right. There's a lot of noise in the hallway, my colleagues at home. Now, to use the T table, we have to know what degrees of freedom means. Degrees of freedom is easy. Degrees of freedom is n minus 1. So how many measurements did we make? 14. What are the degrees of freedom? 13. Okay? So I'm now going to use the Z table. Degrees of freedom is 13, and the value of T is 1.771. Let's jump to the T the student T table. Okay. That's the student table, student T table. Now, make sure I don't make a mistake here. N is 14, degrees of freedom is 13. So the first column is degrees of freedom. Now, I'm going to read across. There it is right there. Looking for 1.771. That was the number, right? Okay. So I look up there, and it tells me alpha is 0.05. Okay. Oh, alpha over 2 to be precise. Sorry, alpha over 2. Alpha over 2 is 0.05. All right, so hold it a minute. In fact, let's look at that shaded area is the number up on top. Okay? That shaded area is the number up on top. Chris, help me out. We had 1.771. So it turns out that the tail on the right-hand side has an area of 0.05. Are we good? Okay. That means, due to symmetry, we're looking for plus and minus. We're looking for the upper and the lower. There's another number right here. And what's that area? The same, 0.05. So the total area of the tails, 0.05 plus 0.05, is 0.1. What's the area between those two numbers? 0.9. 90% confidence interval. Okay? So, we have a 90% confidence interval. Last problem. Another 90 seconds, 2 minutes max, we're out. Okay, determine a 99% confidence interval. Determine a 99%. This is an easy problem. A 99% confidence interval. This is the formula. I'm reminded of my colleague's question. Will we have this formula on the exam sheet? Absolutely. Now, I was looking at my colleagues back over here. We had 90% confidence. So we took 0.1 divided by 2, we got 0.05. Okay? So now, we want to be 99% confident. That means the tails, both of them, is 0.01 area. So half of that is 0.005. Okay? So I now look at the student T table, and I'm going to look under the column that gives me 99% confidence, which is 0.005. What's my degrees of freedom? N minus 1, which is 13. So what we do is we go and we calculate the student T coefficient. Help me out. I'm going for 99%. Is that 0.005? I'm sorry, it's getting late. And 13, 3.012. Did I do it right this time? 3.012, okay? That becomes the T sub alpha over 2. So now, the unknown population mean, I have no idea what it is because I haven't measured everything inside the population, is the sample mean plus and minus the student T coefficient times the standard deviation divided by the square root of n. That's it. We're done. 43.8 plus and minus something. You can write it either way. We've gone through last year's exam from beginning to end, all 9 problems. How did we do? Was this worth it? All right. Good, good. All right, my colleagues, that's it. I'll say good night or good morning, good evening. Oh, we have a question? Are we getting extra credit also? All right, for those of you, and I hope all of you, who will be in my lecture tomorrow, you can remind me.